Hello, everyone. This is Changyang. I'm currently a postdoc in the University of Cambridge. Today, I'm going to present our work, NeuSOS, Neural-Enhanced Underwater SOS Detection. This work was done when I was a PhD student in the Hong Kong Polytechnic University with my advisor, Dr. Yuanqing Zheng. Every year, we can see many sad news about someone drowned in the swimming pool. Actually, drowning has been a public safety concern around the world. Most of us will imagine about the drowning scenario like this. The swimmer will splash and yell for help. Thus, the people nearby can notice him and provide timely rescue. However, in reality, drowning actually is silent and very fast. It is a video clip of a real drowning case. We can see the boy in the red circle is struggling. He wants to call for help, but sinks into the water very fast. Actually, we can see the lifeguard is only a few meters away, but nobody has noticed him because it's very hard for swimmers to make sounds during drowning. So this incident make us thinking about the question, how should swimmers call for help in an emergency? Most currently drowning monitoring systems are vision-based solutions. Basically, they deployed several cameras in the swimming pool to detect if a swimmer keeps stationary at the bottom for a while. If so, it will generate alarms to the lifeguard. Indeed, this method can detect drowning, but the swimmer may already suffocate, after such a long time. And most importantly, using this system, the swimmer still cannot actively call for help in some emergent cases, such as choking and some discomfort. So last year, we had a work named I Call Help, published in Census, which transformed the swimmer's smartwatch into an SOS transmitter. Thus, in an emergency, the swimmer can just press the button on the smartwatch to transmit the acoustic SOS chirps. Then the receivers in the swimming pool will detect this signal and generate an alert to the lifeguard. The basic idea is the smartwatch can transmit acoustic chirps as the SOS signals, and at the receiver side, we can use a clean chirp to perform cross-correlation with the received chirp. Thus, we expect the power of the SOS signals can exceed the noise flow, so we can successfully detect the SOS signal. Because the chirp signal has a very good correlation property, so if there is no SOS signal, the correlation results will be very flat, which means we don't detect the SOS signal. But this is a very ideal case because we assume the noise is Gaussian distributed. But in reality, the underwater noise is very dynamic and it doesn't follow a Gaussian distribution. So the correlation is not always effective. We can see here is a received chirp in the water. We can see most of the noise is below 2.5 kilohertz. So in this case, if we perform the cross correlation, we can see the SOS peak, but we can also see the noise peak is also fairly high. So even though there is no SOS signal, we can still see some high peaks in the cross correlation results. Thus, if we set a very high detection threshold, it may cause the false negative. And conversely, if we set a very low threshold, it may cause the false positive, which is a critical issue in the emergency cases. Another challenge is the bursting noise in the real swimming pool, which means the water pumpers or swimmers, the splashing may cause a very powerful noise in a very short period of time. And similarly, if we perform the cross correlation, when there is a bursting noise, we cannot ensure which one is SOS peak and which is the noise peak. So therefore, in this paper, we proposed a new SOS. It is an SOS detection method with a neural network. We have an observation is that even though the underwater noise and the bursting noise will impact the cross-correlation results, but we still have an opportunity to detect the SOS signal from the spectrum. We can see the underwater noise. It's very powerful, but it is mainly distributed in a low frequency part. But we can still see, part of chirp in the high frequency range. And the bursting noise, we can see it's very strong, but it lasts only like for a very short period. So we can always observe a part of SOS chirp. Thus, we can use the deep learning to detect the SOS chirp pattern in this spectrum. So in this case, we transform the signal detection problem in the audio signal into an object detection task in an image. So to facilitate the neural network to detect the chirp pattern, we incorporate some physical information into the deep learning. So we first apply the rhythm transform, which can project the image to different angles. Thus, we can intentionally magnify the chirp pattern. We can see after rhythm transform, if there is a chirp with 45-degree slope, so there will be a bright point at 45 degree. So we can get the neural network to find this kind of chirp pattern. Here, we use the rhythm transform as an input. Another input is the spectrum. So to get the neural network to learn this kind of chirp pattern, we design an untrainable CNN kernel with the same slope as the chirp. So during the convolution process, it will scan the whole spectrum and match the chirp pattern. Because this kernel actually is untrainable, so the output will enhance the chirp pattern and blur the other noise type. Therefore, we can somehow regard it as a signal denoiser and enhancer. This is the feature map of each CNN layer. So the first row of this figure is the output for the SOS signal. We can see initially the SOS chirp is very noisy, but after 5 layers, the output has a very clear chirp pattern. In contrast, for the noise output, we can see it has no such a chirp-like pattern. So the neural network can effectively capture this pattern and detect the SOS signal in the noisy spectrum. Okay, we conduct the experiments in a swimming pool during the operation hours. And we can see many people are swimming nearby, which may cause some kind of splashing interference. Our user is here wearing a smartwatch to simulate the drowning movements. We also deploy an acoustic receiver in the swimming pool to receive the SOS signal. That is the evaluation results. The left figure is the confusion matrix of the SOS detection. We can see the overall accuracy is about 97%. And the right figure is the receiver operation curve, ROC curve, comparison between our system and the traditional cross-correlation method. We can see the new SOS outperform the cross-correlation by about 9% with the same false positive rate of about 1%, because our system is more robust to the dynamic underwater noise and the strong splashing interference. So for more technical details and the evaluation results, please refer to our paper. Okay, in conclusion, we want to attract your attention that drowning actually can happen even with the professional lifeguard presence. And we proposed a new SOS. It is a robust underwater SOS detection system that can detect SOS signal in the dynamic underwater noise and the strong bursting interference. We also develop a signal-aware deep learning module to capture the SOS chirp pattern, so it outperforms the traditional cross-correlation methods by a larger margin. Okay, thanks. That's all for my presentation, and I welcome any questions. Thank you.